We're going to start with differential equations. And our objective is to solve, normally systems are going to come from biological, physical, engineering applications. And a lot of them are governed by differential equations or partial differential equations. And so our objective is to solve all these or learn techniques to solve these things. Okay? So in some sense, the most abstract representation or some representation of such dynamics might be written in some form like this. This is going to be where we're going to start and figure out how to solve such an equation. What this says is I have some quantity y that evolves in time, maybe with some complicated function f. So here's the right-hand side of this function. And I'm interested in what happens in y as a function of time. Okay? Now, y could be a whole bunch of different things. You could have I should pick easy, meteorological data. It's early in the morning still. The tongue isn't quite loosened up. You could have something like heat flow. You could have populations of species. You could do almost any kind of thing where things are changing in time. And part of what you would like to do as a scientist, right, is you'd like to say, I'd like to learn how to solve this so I can make prediction, like make models for my system. And I want to make predictive powers. And what you also need in this system is to say, not only do I want to see how this thing evolves forward in time, I have to start, to be able to answer that question, I need a starting point. I need to say, and my system is initialized at, is specified at some point in time. So you might say, I have some initial condition, like this. All right, so there you go. We're predicting time and evolution. You take a differential equation, you say, I want to understand how this thing evolves, given that I know the state of the system at a given time. So the question is, how do you go about solving that? Okay? So what we're going to start with is, in fact, so numerics is interesting because if you take a look closely at it, you're going to basically go back to freshman year of college, let's say, or even high school. We started learning calculus. And the whole point of calculus was what? You started understanding this idea that if I take differences in times of things, and I take that difference to be smaller, 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 and I go to the limit where it's infinitesimally small, I get this thing called a derivative. Well, the first thing we're going to do in solving equations is say, forget what you know about calculus, because in fact, calculus creates a problem for you, because there's a divide by zero. Let me show you this divide by zero and what we're going to do with it. Okay. So let's talk about this. Here's the problem, dy dt. And let's go back to what the definition of derivative actually is. Here it is. All right. dy dt is equal to the limit as delta t goes to 0 of, I'm going to represent like this, some delta y delta t. Some small change in y, small change in t. So we learned this like from a slope formula. Okay? And the idea was, hey, there's this process by which delta t goes to 0, and we have this quantity, what we call the derivative, an instantaneous rate of change. Okay? Now, here's the problem with the computer. You say, I'd like to calculate a derivative. But it goes like, well, okay, so first of all, this is hard for it to think about doing, taking things to be infinitesimally small. What the computer does is adds, subtracts, multiplies, divides. That's it. Okay? And so let's talk about dividing. You're telling it to divide by 0. Now, truth be told, really you're not dividing by 0. You're dividing 0 over 0, but in such a way that it makes sense, right? This is, remember L'Hopital's rule, right? There's like you get these zeros over zeros that didn't make sense, so you had to go make sense of it. Well, the computer just goes, look, I have a 0, divide by 0 problem here, and you gave me junk. I'm going to give you an NaN back. Not a number. Okay? So there's a problem there. And so instead, this is a little extreme. Delta t goes to 0. Why don't we just say small? Right? Everybody okay with that? It's a little bit of a cheat. It's not quite right. But if delta t is small, not 0, maybe everybody will be okay with that. And so what we're going to do is going to say, how about if instead I just say, well, you know, I'm going to say that what I want to do is say, instead of saying, thinking about dy dt is equal this here.